Welcome everyone. Today I will talk about the discovery of a new diamonds and gold deposit, a MESOARCHEAN pebble conglomerate from the northern slave Craton, and what their implications are for Craton evolution, when and to what extent Earth's Cratons became underpinned by thick lithospheric mantle roots capable of hosting diamonds, is one of the most controversial aspects of Archean geology and geodynamics. Alluvial diamonds from Archean sediments can be used to address this argument. We report the recovery of 3 diamonds from gold-bearing MESOARCHEAN conglomerates in the northern slave Craton that allow us to provide constraints on the minimum age and the thermal structure of its mantle roots. This study is a team effort between the University of Alberta, Penn State University, Laurentian University, University of Padua, the SRC, and with funding from Silver Range Resources, NSF, Canada Excellence Research Chairs, and the Metal Earth Project. The people involved and our institutions are provided at the bottom part of this slide. In collaboration with Silver Range Resources, the Metal Earth Project, Nunavut Government, and Penn State University, and with information of our co-author Valerie Jackson, a team went up far north in Canada for field work in the northern slave Craton, and the field work area is indicated by the orange circle up in Nunavut, close to the Coronation Gulf. This region had previously been identified as having significant gold potential by a number of companies and is under active evaluation by Silver Range Resources. 15 kilograms of rock was sampled, as you can see the pebble conglomerate in the middle, and this was sent off to the SRC for diamond recovery, and 3 diamonds were recovered, as you can see in the image on the slides. Research on the diamonds was subsequently done at the University of Alberta and the University of Padua. The diamonds we have found so far are small and not economic, but they occur in ancient sediments that are an exact analogue of the world's biggest gold deposits in the Witwatersrand Basin in South Africa. 40% of the world's mined gold comes from the Witwatersrand. Both the new Canadian diamond gold deposit and the Witwatersrand gold deposit contain quartz pebble conglomerates, have carbon material present, are MESOARCHEAN in age, and contain diamond and gold. Diamonds and gold are strange bedfellows, as diamonds are brought up from deep in the mantle to the surface by kimberlitic magmas and associated magmas, whereas gold deposits form when heated fluids circulate through gold-bearing rocks and concentrate gold to deposit in new locations in the crust. Erosion of diamond deposits and gold deposits can result in a new alluvial deposition where the diamond and heavy gold falls out in stream beds. The diamond gold deposit was discovered in the northern slave Craton in Nunavut, as indicated by the yellow circle. Across the slave Craton, previously, peridotite and sulfide have been analyzed for rhenium-osmium isotopes and have shown rhenium depletion model ages up to 4 billion years, with a main peak around 2.7 billion years, as you can see in the diagram on the left. The slave Craton geology also reveals a main age peak at 2.7 GA, which has been related to the convergent tectonism and the accretion of juvenile terrains to the central slave superterrane at about 2.65 GA. The age of the lithosphere, however, is far more contentious, especially the proportion that was MESOARCHEAN and in the diamond stability fields. The zircons we analyzed from the new deposit show a narrow peak with a minimum age depositional age of 2.85 billion years. When only using the zircon data that are within 95 to 105% of Concordia and had at least an integration time of 15 seconds, we see that the minimum age is 2.85 million years, as shown on the radial plot on the left. As shown on the graph on the right, the majority of the data is centered around 2.94 billion years, and the zircons show a very restricted age range, as is highlighted in pink. When there is a small catchment, it is likely only a limited number of geological units are sampled, particularly in an active tectonic regime, There is often a rapid new exposure of potential source rocks and mostly local sources in an active basin. Pebble conglomerates are high-energy deposits formed in proximal sedimentary facies, and thus the type of our deposit alone indicates a small source. A small catchment results in a narrow range of ages in a histogram, as is visualized on the left, whereas a large catchment is likely to sample more geological units and results in a wide range of ages in a histogram. As we see a narrow range of zircon ages, the ZIRCON geochronology also points to a small source for the diamond gold deposit. The zircon hafnium isotope data also shows a limited variation, further supporting a small source of the diamond gold deposit. In the diagram, the initial 176/177 hafnium ratio is plotted versus the 207-206 lead age. As you can see, the majority of the data centers around 2.94 Ga and has an epsilon hafnium of 0. No significant negative epsilon values are present, indicating there is no reworking of old crust in the source of the zircon. Some slightly positive epsilon hafnium values indicate the presence of some juvenile material. For data that fall outside the 95 to 105% of Concordia, and with low integration times, lead loss is present, as is indicated by the grey arrow. The sampled rock that was delivered to the SRC was processed by Christiana Merceau's team at the Saskatchewan Research Council, where they used certified techniques to recover diamonds. The 3 diamonds have cubo and octahedral morphologies, as indicated by the top 3 photos. They also have cubo and octahedral growth structures, as revealed by cataluminescence images in the bottom 3 figures. In one of the diamonds, an olivine inclusion of less than 20 microns was present, and this olivine inclusion also shows that these diamonds are not synthetic. The carbon isotopes were also analyzed for these diamonds. Carbon isotope values are expressed as delta 13C and are the 13/12 carbon ratio of the sample relative to the 13/12 carbon ratio of the Vienna PD belemnite standard. The mantle carbon isotope composition is around -5 per mil. As you can see, the peridotitic diamonds fall in that mantle range, whereas eclogitic diamonds have a far larger range from about -40 per mil up to +5 per mil. These are caused by recycled material. In the lowest panel, you can see organic carbon and altered oceanic crust extend down to very negative values of around -40. In the lowest panel, you can also see that carbonates have much more positive values. Rayleigh fractionation of CO2 or carbonate oxidizing fluids can also result in slightly more positive values, whereas diamond precipitation from a reducing fluid results in progressively more negative carbon isotope values of the diamonds. When we now look at the slave craton and our samples, we can see that the macro diamonds from Penda mostly fall around the mantle range of -5 per mil, whereas the micro diamonds from Penda have a heavier mode. Our samples are indicated by the orange rectangle, and they show that they fall on the heavy side with values of -0.3 to -3.5 per mil. This shows that our diamonds are picking up this heavier signature and come from oxidizing fluids or have an influence of carbonate subduction. Sample numbers are limited, but we may potentially be sampling a restricted population from a restricted source. And our samples have very different carbon isotope values than synthetic diamonds, which, as you see on the left, extend from -30, 35 per mil down to -75 per mil. So again, showing our samples are natural diamonds from the mantle and not synthetic. As the zircon show ages from 2.84 up to 3.5 Ga, our diamonds could potentially be up to 3.5 Ga. Based on the oldest diamonds to date that are from Penda with 3.5 billion years, and the deposit ages of the zircons that we see, it is unlikely our diamonds resided in the mantle for much more than 700 million years. We made a conservative assumption of residence times of 10 million years to 1 billion years. When using the temperature-dependent nitrogen aggregation, as shown in the top figure, where nitrogen aggregates from single nitrogen to pairs of nitrogen to 4 nitrogen around the vacancy in the diamonds, we can use this to estimate the temperature range of diamond formation. And our samples show up to 1707 atomic ppm nitrogen in the form of 2 pairs of nitrogen. And this results in a temperature range of 1060 to 1170 degrees Celsius. Single crystal XRD was subsequently applied to the olivine and reveals residual pressure exerted by the diamond host. Elastic thermobarometry allows us to estimate with surprisingly tight bounds the depths of which the inclusion was trapped in the diamond. Using the measured volume of the olivine plus an Archean olivine mantle composition of a magnesium number of 92 to 93, the equation of state and the above temperature range of 1060 to 1170 degrees Celsius, we can confine the pressure to 5.5 to 5.9 GPa. On the pressure versus temperature plots, our pressure temperature estimate from the diamond is plotted in orange. This results in a cold geotherm of around 38 megawatts per square meters. As you can see, this overlaps with the cold geotherm from the slave craton, which is displayed in brown symbols. The slave geotherm is determined at around 50 million years when most of the kimbolites erupted and thus yields the last equilibration temperature and depth of the xenoliths. As you can see, the cold geotherm at 2.84 billion years or even older shows a similar cold geotherm to the one recently at the slave. So this poses the question if the Archean mantle was really much hotter than today. And previous studies have estimated that the Archean lithospheric mantle was up to 250 degrees Celsius hotter than the one today, as you can see in the figure on the left. However, our diamonds indicate cool mantle roots had already formed in the Archean that are as cold as today. So was the surrounding ambient mantle really that much hotter? Depending on how data is filtered for iron-titanium ratios or the redox state, and including a sampling bias by oversampling of Archean komatiites or not, the potential temperature of the ambient mantle varies. In the titanium-dependent conditions, a possibly slightly higher temperature in the Archean is visible with about 150 degrees Celsius, which is much less than the 250 degrees Celsius previously estimated, as you can see in the top figure on the right. When using constant redox conditions, as in the lower panel, the temperature decrease since the Archean is even less. So this dataset suggests that the Archean and Proterozoic mantle may not have been so hot. Davis et al. In 2003 proposed that the widespread mafic magmatism at 2.7 GA in the central slave superterrane and the late Neo-Archean granites cannot be reconciled with preservation of a continental lithospheric mantle with diamonds that is older than 2.7 billion years. Davis suggested that the development of the east-northeast structure in the slave craton formed in the Neo-Archean. Older mantle components would have been emplaced by tectonic underplating during Neo-Archean collisional events. However, there is evidence for a Mesoarchean lithosphere and diamonds under the superslave superterrane, shown by Olbach and Westerlund. While the 3.5 billion year isochron age of Panda diamonds has been suggested to be a mixing line, other xenoliths and diamond ages are present at 3.2 GA. And Helmsted's proposed in 2009 that the Mesoarchean lithospheric roots was already coupled to the Mesoarchean crust of the central slave superterrane before the accretion of the Neo-Archean terrains. Part of this Mesoarchean roots must have survived the Neo-Archean breakup of the central slave superterrane and the post-accretion, plutonism, metamorphism, and deformation. So our diamond and zircon data show a Mesoarchean crust and a thick lithosphere in the northern parts of the slave craton. Previous studies have shown models for both a vertical and horizontal accretion to form thick cratonic lithosphere. Stacking of cold lithosphere is the fastest way to build a lithosphere keel, and we suggested in the Mesoarchean small but high aspect ratio cratonic fragments with deep lithospheric keels were present and coupled, as shown on the left. So we did not only have a Mesoarchean keel in the central slave superterrane, but also one in the northern slave craton. These were subsequently amalgamated into a larger craton with a wide and deep lithospheric roots, as you can see in a schematic way shown on the right. So in summary, there is a new diamond and gold bearing quartz pebble conglomerate deposits discovered in the northern slave craton. And the presence of diamonds in this gold bearing conglomerate reinforces the similarity to the largest gold deposit in the world in the Witwatersrand basin in South Africa. The zircon ages and isotopic data indicate a small catchment and source area. The diamond pressure and temperature estimates, in combination with the age constraints, reveal a cold Archean, Mesoarchean mantle root that is as cold as the coldest mantle roots today. In the Mesoarchean, small cratonic nuclei with deep lithospheric roots were already present, and more work is ongoing to find more diamonds. So finally, we would like to thank the Canada Excellence Research Chairs, Metal Earth, NSF, and the Saskatchewan Research Council for funding, Dave Olesen for floatplane logistics, and Mike Power of Silver Range Resources. Thank you.